Hi, everyone. Thanks for joining us today. My name is Galen Maclaurin. I'm the group manager for geospatial data science at the National Laboratory of the Rockies. Um, Joining me today is Gabe Zuckerman. Gabe, let you introduce yourself.
Thanks, Galen. Yeah, excited to be here today and excited to talk with you all about our really cool tool, reV. Back to you, Galen.
All right. So jumping into this, I want to start by framing the importance of this model by thinking about electricity demand and how it's changing and changing rapidly. So for, the 15 years before the pandemic, annual energy electricity demand grew at less than 0.5%. Since 2020, that has rapidly changed. And so this has really changed the environment that everyone in the power system is working. The developers building generation, the grid operators, the utilities delivering. Um, in the top left here, we have historical data with a little bit of projection from EIA. And as you can see there, data centers is really an important piece of this. In the line, the top line, the commercial line, we're seeing 2.6 percent growth in that commercial sector, which includes data centers. We're also seeing a lot of growth in industrial from increase in manufacturing. In the bottom right is some projections out to 2050 from Evolved Energy Research. And all of the data that we have as far as data centers that are being permitted, that are under construction, is that we're going to see a rapid growth in the demand driven by these facilities, small footprint facilities that can really consume massive amounts of electricity. So as we move into the future, we're expecting to see upwards of 25% or more annual growth in demand, specifically coming from that data center sector. And so, these projections, we're going to come back to this at the end to talk about how the model that we're developing is really relevant for looking at this demand. Next slide, please. So as we have rapid growth in electricity demand, this requires obviously more generation and more transmission, which creates siting interconnection challenges. So every year this becomes more and more of a challenge. We're seeing very long interconnection queues, 3 to 7 years across the US, increasing siting challenges. Where you have more and more generation being built closer and around communities, the need for new transmission lines, which, as you all know, are very hard to build and take, 10 to 20 years. So this is just to kind of frame some of the really important fundamental challenges in the landscape in which we have developed this model to support the power sector very broadly, to address specific questions that to really help us support this growth in demand that needs to be met by new generation transmission. Next slide, please. So to introduce you to the reV model, this is an open source geospatial platform developed at the National Lab of the Rockies. This is a model that we've designed to examine both the barriers and the opportunities to deploy energy assets. The modeling spaces that this model is in is between land availability and siting constraints, grid interconnection, and system performance and costs. So this is kind of your Venn diagram of the geospatial modeling spaces in which we're focused for this model. So this model asks some key research questions. For example, how do social, ecological, and technical considerations impact energy siting? How do spatial dynamics of system performance, costs, and interconnection drive deployment? And to what extent can these constraining factors be mitigated through cost reductions, technology innovation, and careful siting? So, three kind of broad research questions that we focus on. Obviously, there's a lot in there. Next slide. So why is reV uniquely suited to answer these questions? First and foremost, this is a multi-resolution geospatial model that allows us to take very, very granular geospatial data and represent that detail at scale. So this model operates from regional to national to even continental scales. but we are able to represent the native data resolutions of things like building footprints, roads, streams, transmission right-of-ways, all of these features that the actual footprint of where they are is really important for siting. But then we need to represent that at the national scale. So we're able to integrate this across the different resolutions of the model. And we're going to go into this in a lot more detail so that'll make more sense. The model also integrates very large spatial temporal resource data sets, such as NLR's Wind Toolkit or our National Solar Radiation Database, which are multi-terabyte data sets that represent the spatial and temporal dynamics of the resource. Um, the model can integrate very effectively technology and cost insights. So we can parameterize a different technology. So, for example, a different wind turbine configuration at each site that we're modeling across the entire country. So it gives us a lot of flexibility to really apply the right technology that would be deployed at a location. It also allows us to look into the future and ask some questions about, what technology innovations are we seeing coming into the market? What are we seeing as far as cost reductions? And that helps inform where additional R&D investments are going to be the most impactful. And then lastly, seamless integration with other models. And so the reV model couples very closely with two modeling spaces in the bulk power system: capacity expansion modeling. So for example, EI's NEMS model or NLR's REIDS model, and production cost and stability modeling. So for example, models like Plexos or NLR Sienna model. Also couples with a lot of other models such as distributed generation and many others. But these are really important because this is the space that we work in. This Powered by series has highlighted the REIDS model and the Sienna model. So I encourage you to go back and look at those, and that'll really help you kind of understand some of the connections that Gabe and I are going to be talking through here. Next box. So what are the specific outputs of the reV model? So I just want to kind of foreshadow where Gabe is going to talk through in a lot of detail, but what does the model give us? So the model is foundationally a technical potential model. So it estimates what is the total available land and the generation potential given a set of technology and land exclusion assumptions. So think of this as the ceiling for the amount of potential generation that we have that you can then look at through different scenarios, which we're also going to talk about in more detail. Um, it has a very robust transmission routing and cost algorithm that we're going to talk through as well to estimate the distance and interconnection costs for what we call spur lines. We'll reference that term a lot. This is the generation tie line that connects a new generation asset to the existing transmission system, to tying into a line or tying into a substation. And then the kind of main output that we publish that are then fed into capacity expansion and production cost models are what we call supply curves, and we'll also talk about those in a lot more detail. But this gives you a sense of where do we have potential capacity at what costs, and it also provides time series generation profiles at all these locations. As I mentioned, Wind Toolkit and the NSRDB solar data, we're able to generate hourly or even 5-minute generation profiles that we can pass then to downstream models. Last box here. So who are the users and stakeholders of this model? A lot of different stakeholders, but really the people that we interact with the most are in these kind of three areas of energy planners and developers. So ISOs, RTOs, utilities, work a lot with state and local governments. And a big one, really important one, is project developers and just kind of large energy companies, transmission companies as well. They're the ones that have started to really pick up this tool to use in screening where they're looking for their next projects. It helps them understand some of the constraints and where they're going to have the easiest path forward as far as getting access to land and building projects. Energy analysts. So this supports a lot of research at universities. Graduate students love using our data. It really helps. And so this is really important that we're feeding back into that community as well. Work a lot with other national labs as well. and other FFRDCs. Those are federally funded research and development centers. A lot of energy consultants we work with, and they use our data as well as R&D nonprofits. And then lastly, the federal agencies are really important. So obviously, the Department of Energy stewards our lab, provide the majority of our funding. So we work very closely with them on the priorities that they have and how this model can really inform the federal government. We also work very closely with land management agencies such as the Bureau of Land Management, the U.S. Forest Service. We work with the Department of Defense, EPA, BOEM, Fish and Wildlife, and so several others as well. We have engagements with all of them, and so we really want to understand kind of what are the pinch points that they're feeling as far as managing the land that they're in charge of, to make the most of opportunities for energy deployment. Next slide. Okay, so let's get deeper into this. So what does reV do? So like I mentioned, it's tech and potential and has transmission interconnection to produce these supply curves. And let's look at this figure first on the left. So this is what I mentioned about the multi-resolution and the detail at scale. So if you look at the bottom inset on the right, you see, a rural area where you have a road network, you've got some streams, and then you see those building footprints. So this is really where the detail at scale is so foundational. So we are able to model setbacks, and we're going to talk about this in a lot of detail, from these features. Different features have different setbacks in different places, and we're going to talk about ordinance as well, how they feed into this. But this model is set up so that we can have very high fidelity in the way we're representing these individual features, but then wrap that up through aggregation, an intelligent aggregation to represent that at the national scale. So as you look at the detail area on the left, you're kind of zooming out, you're seeing that kind of landscape scale, and this is just representing one part of the lower 48, the CONUS. This is just an example of a geothermal data set that we use, temperature at depth, but you're also seeing the transmission lines with their line ratings on there. So what technologies do we model? On the right is the current list. We have fully built out geothermal, pump storage hydropower, utility distributed solar, land and offshore wind, and our transmission routing. Data centers is an emerging area, but we actually just published a slide deck that we're going to reference and I'll talk about a little bit at the end. And just a little bit of a teaser, we are getting started on modeling natural gas, as that's an important part of the power system. And that's going to be the go-to power source for data centers for on-site generation. So we're working on both of those together at the moment. Next slide. Okay, so this model fits into this broader ecosystem that I already alluded to, already mentioned here, but just want to call out a couple really key pieces here. Work across NLR, so you are familiar with the other projects and models that are coupled, very tightly coupled. So first, as I talked about earlier on, we're pulling in these very large resource data sets, so wind, solar, geothermal, spatially explicit data sets that often have time series components to them. Our model essentially batches the system divisor model. So NLR has developed SAM that models system performance and costs across many different technologies, and it's a very computationally efficient model. And so, we can estimate the system performance and costs for, wind plant or solar plant essentially instantaneously. And so that allows us to do it millions of times. And so we have direct model coupling with the SAM model. We're also going to talk a little bit about Compass, which is a new LLM model at the lab that is scraping ordinances from the web. And then we can parse through the language in those ordinances and we can translate into what that means geospatially on the ground. For example, setbacks from buildings for a wind turbine, the classic example that we can model in reV. So that's all feeding into reV. reV is a high performance model. It can run on the cloud. At the lab, we run it on our high performance computing system. And this is why, like I mentioned, SAM being so quick is really important, that we can run this model for the entire country. And, it takes like an hour for us to run a full technology. So it's extremely efficient. The outputs of this model, since the beginning, we've had a very tight coupling with reads. Reads, the spatial granularity underlying reads comes from rev. So we developed the supply curves that represents all that detail that I just kind of gave you a high level overview, and then is aggregated into reads, which is a zonal capacity expansion model. A new, fairly new model connected to reads is the resource adequacy model, PROS, the probabilistic resource adequacy suite, which allows them to look at a lot of different parameters and vary those and look at what it does to resource adequacy. And then often in a lot of our modeling, either we'll go directly from rev to Sienna, or a lot of times we'll take the outputs from reads, and those will go into Sienna. Sienna is a production cost modeling and a stability model developed at NLR that allows to integrate a lot of data from PSSE raw data formats to represent nodes on the grid and the data about the operations of the grid, and do production cost modeling as well as stability modeling. And so that's an important tie is Sienna needs very high resolution generation data. And so that's produced from rev. So we'll produce like 5 minute generation for wind and solar, for example, and that can be fed directly into Sienna. So they have very high temporal resolution of those generation assets. All right. Next slide. Over to you, Gabe.
Yep, thanks, Galen. And so after that high level overview, I'm going to give a little bit more detail on the steps in the rev pipeline and walk you all through how rev actually produces the supply curves. So as Galen mentioned, rev starts with resource data, in this case, geothermal or temperature at depth, but they could be wind speed or solar irradiance data. We pass that through our system generation model, or SAM, as Galen mentioned, and in this case for geothermal, it's coupled with GENM, or the Geothermal Electricity Technology Evaluation Model. And it batch computes capacity factors and costs at hundreds of thousands to millions of sites across the country, depending on the data set. Could be at a 2 to 4 kilometer spatial resolution for every hour of every year for 20 some years, could be even as much as every 5 minutes of every year. And so once we have our capacity factors and cost estimates, we aggregate this information into a larger grid cell or a representative site, aggregating cost and energy production information. And at that level, we apply siting constraints or development barriers that Galen was alluding to understand not just the quality or cost of the energy, but also the quantity or availability of the resource. And finally, we connect that representative site to the grid by estimating costs for gen-tie spur line, substation, and any network upgrades required to get that power to the load centers. And with that, we have costs, including site-based energy generation costs, transmission and interconnection costs, usually presented in a levelized format, like levelized cost of energy, and hourly or sub-hourly generation profiles that can all be used to either inform downstream models like Galen was just talking about, or as a standalone data product. And from here, I'm going to walk through some of the key data or methodologies for this process. So I'll start with a little bit more detail on our resource datasets, which lie at the foundation of rev. Here, we're showing some of the technologies and resource datasets that rev leverages. On the upper left, we have an example of our geothermal resource, which is temperature at depth, in this case, 4 kilometers. Our resource dataset is the Stanford Thermal Earth model and goes down to 7 kilometers below the surface at about a 4 kilometer spatial resolution. On the top right is an example of our pump storage hydropower resource, which is the modeled resource capacity of a linked reservoir in a closed loop system. In the lower left, we have our solar radiation database, or the NSRDB, which has hourly solar data from 1998 all the way to 2024 at a 2 kilometer resolution, with some years as low as 5 minutes. And in the lower right, we have our wind resource data, the wind toolkit, which has hourly and as low as 5 minute data from 2007 to 2013, and some as low as 5 minutes. And again, these are the foundation of the rev model for energy generation and costs. So now I'm going to move into our siting, and resource potential assessments stand at the intersection of multiple disciplines, and to accurately quantify potential, local siting constraints are a key consideration. These that I've listed here, like defense and airspace, social and regulatory, environmental, technical and topographic, are really, really key. And woven together, these siting constraints can impose substantive limits on development and deployment opportunities, but sometimes can be difficult to comprehensively assess at a national scale. And to incorporate the uncertainty, we often use a scenario modeling framework with varying levels of siting restrictiveness, often with an open access scenario, a reference access scenario, and a limited siting scenario. And I'll walk through some of the examples of the types of data that we use in each of these categories here. So here are some defense and airspace considerations that we often include in our siting, such as with airports and heliports applied to a number of different technologies like geothermal, pump storage hydro, wind and solar, radar line of sights, Department of Defense lands, and risk adverse impact on military operations readiness areas, or RIMORA, which we apply to wind. These are just some examples, and we apply a number of others that can be found in our documentation online. Um, some environmental, technical, and topographic considerations that we incorporate are water and wetlands, which again, we apply to a number of different technologies, threatened and endangered species habitats, and slope and terrain restrictions. Additionally, we account for protected areas, different types of habitat for sage grouse and prairie chickens and bats, as well as big game. And again, we apply these differentially depending on the siting scenario. So we might have fewer for an open scenario, but more restrictedness in the limited scenario. The last area that I'm going to talk about is the social and regulatory considerations, and many social and regulatory siting considerations come from ordinances or local laws that regulate the placement of, in this case, energy assets, often relative to existing infrastructure as setbacks. For example, there might be setbacks from structures or buildings, roads, transmission, rights of ways, and hydrological features. And as you can see here with the black color on the map, can have significant impact on developable land availability. And setbacks and the ordinances that govern them are a rapidly evolving body of laws that have been expanding over the last decade. In fact, we first conducted this collection of ordinances back in 2018 and then again in 2022 manually by hand. And these efforts were incredibly labor intensive, with taking over 1,500 hours of work. At the same time, they were incredibly impactful. They led to one of the lab's most viewed nature energy papers at the time, and really changed the way we think about the spaces and places we can site energy assets. And ordinances and the setbacks that are from them have tremendous impact on availability. Again, from our 2022 Nature Energy paper, we found that they could reduce up to nearly 90% of available area for wind and 40% for solar. And these data sets, when we published them, the 2018 and 2022 collection efforts created massive interest from developers, regulators, policymakers, and energy modelers across the states, because it was a first of its kind data set that comprehensively and spatially detailed with this much comprehensively and spatially detailed a data set like this to exist. And it also got some buzz in the public media, which was nice to see. But given the rapid expansion of these ordinances, we couldn't repeat the manual data collection again. So we started to think about ways we could leverage LLMs to help with this. And so, as Galen mentioned, we put together a model called COMPASS, which stands for the Continuous Ordnance Mapping for Planning and Siting Systems, that scrapes and retrieves ordnance data from the internet, then formats that into structured machine readable formats at various spatial resolutions or jurisdictions. So at the state level, county level, and even in some cases, municipality, township, or city level, that can be then geospatialized. So I'm going to walk through this slide now. On the left-hand side, you can see the number of ordinances we collected in 2018, which we found about 300. Then again, in 2022, we found nearly 2,000. And then in our 2025 collection, we found over 12,000 ordinances. And you can see how much they've continued to grow. It's not just the number and locations of ordinances that are changing and growing either, but it's their impact and it's their impact. And the middle figure shows that. So on the bottom here, in the middle, we see our noise ordinance collection, and noise ordinances are typically the maximum decibels acceptable at a residential location. In 2018, we found about 40 noise ordinances with a maximum level of 55 decibels acceptable. In 2022, we found nearly another 200 with a more restrictive 50 decibel limit at residential locations. And then in 2025, we found nearly 700 more with an average of 50 decibels at residential locations. And we recently published another paper in Nature Energy investigating this, and we found that sound impacts can be significant, as much as nearly 30% additional area from after accounting for other setbacks. It can exclude up to nearly 30% of additional area after accounting for other setbacks. But I'll touch more on sound in a bit. Above that, we can see how structure ordinances or building ordinances have changed over time, with nearly 70, we found slightly over 70 in 2018, 300 more in 2022, and nearly 900 more in 2025. And what's really important here is the geographic context, which matters a lot when interpreting the impact of the setbacks. The panel on the right here shows two instances, both with 750-meter setbacks from buildings, but depending on where you are, that's going to change the amount of available area drastically. On the top here, you can see a county in Wyoming with significant available area, whereas in the county in Pennsylvania, there's very little available area, even with the same 750-meter setback. And all of this ordinance detail and geographic context is incorporated into the siting engine of reV. And it's not just the structures and noise ordinances, but also local laws, local setbacks required by local laws for transmission, water features, and railroads. And all of this detail at scale that requires millions and millions of spatial computations is part of the siting engine of reV. And so now I'm going to switch gears slightly. We've talked a lot about siting, but I'm going to walk us through how we consider transmission and interconnection within reV. So reV models the least cost route typically from the supply curve point to the load center, considering two things roughly. Point of interconnection costs, which are broken into the routing of the spur line or the generation tie line, which connects the energy asset to the grid. And we route that using natural and cultural siting barriers, frictions, and mitigation costs with costs that vary depending on the cable voltage and polarity, as well as the type of land or land composition. So for example, it's going to cost more to route through a mountainous area as compared to farmland. And so once we have the cost and route of the spur line, we account for any upgrades, any substation upgrades that are required, as well as any network upgrades that are required to move the power from the point of interconnection, the substation, to the load center where the power is needed. And so I would just take a moment to mention as an aside, we're thinking about ways that we can leverage this framework, this linear feature routing framework for modeling natural gas pipelines. So moving back to the transmission space here, the image on the right shows the results of the process that I just outlined. When applied to tens of thousands of route grid cells across CONUS, we get what's seen here, which is essentially the cost to tie into the grid for an energy generation facility at any given location. And we can see how much the cost varies spatially across the country. And I'd note that the units are in hundreds of thousands of dollars per megawatt. Putting it all together, we have the site-based cost of energy, which is based on the capacity factors from SAM, transmission costs from the reV routing approach that I just walked through, and the capacity, which is determined by the siting engine that takes into account land use, environmental and terrain considerations, as well as ordinances. And this results in a total levelized cost of energy and capacity for each of the tens of thousands of sites in CONUS. And so to put them into a supply curve, we sort them by LCOE and cumulative capacity. Each point on the supply curve or representative facility also, as Galen talked about, comes with an hourly or sub-hourly generation profile of capacity factors for every year that the resource data spans. And all of this is modeled just within one rev run, and it takes just an hour or so on our supercomputers to run, or you can also run it on AWS or the cloud. And again, this can be a standalone data product or passed to a downstream model. And so now that I've given you a detailed look at rev's current capabilities, I'm going to give a sneak peek at some of our upcoming capabilities. So I'll start with some of our advanced transmission modeling work. If you recall from a few slides back, we utilize a least cost path framework for routing spur lines and transmission cables. However, in the real world, the least cost option is not always the most viable option. And so we built a tool to assess the trade-offs when considering multiple options for routing transmission cables. In the image on the right, we evaluate different levels of avoidance or tolerance for areas with natural and cultural risk. In the map, on the top, scenario 1, which is mapped in orange, is the least cost option to move from these 2 points shown here. Scenario 2A, mapped in purple, has a low level of avoidance for these high risk areas, while scenario 2B, mapped in green, has a high level of avoidance for these high risk areas. While there might be additional costs associated with the longer route, 2B, shown in the green here, and in panel C, it reduces the amount of land use in areas that might cause additional delays in permitting that are since they are high natural or cultural risk by nearly 2/3, as you can see in panel B, with a greatly greater reduction in area in these high risk areas. Another aspect of reV that we're developing could help reduce timelines for the transmission and interconnection process is an interconnection cost supply curve. And as I mentioned earlier, we currently model interconnection costs geospatially, um, meaning that the first, and statically, meaning that the first gigawatt to connect to one point of interconnection might actually, in the rev model, might have the same cost to connect as the 10th gigawatt, which is not really reflective of reality. And to help address this issue, we're creating power flow informed interconnection costs that change over time as new capacity is connected within a region. And so we illustrate that in this figure here shown on the right. This particular region has about 7 gigawatts of available interconnection capacity without any upgrades. And so we've developed a model that estimates the costs associated with specific transmission or grid system upgrades that enable each additional megawatt of capacity to be interconnected. And this can ultimately can create a much more highly informed version of the total cost of building and interconnecting facilities. And so this is new work that we're really excited about. The last frontier of reV that I'm going to walk you through is how we leverage GeoAI to account for the impact of sound ordinances to win technical potential. I mentioned I'd come back to this earlier, so this is it. So we have a pretty complex approach for modeling sound ordinances and wind. So we start with a surrogate machine learning model, which we trained on a physical sound model to create the setbacks required to meet the various sound ordinances across the country. These vary greatly across space, depending on the residential building makeup and the topography. And so we combine these spatial setbacks with our bespoke plant layout optimization, which, given all the siting constraints, including the sound, finds the optimal balance of the number of turbines and their placements such that costs and wake losses are minimized and energy production is maximized. So we combine the machine learning sound with the plant optimization to create the optimal layouts given sound. And our first take at this, as shown in the middle image, was to ensure that the noise from no single turbine violated the maximum threshold set by the local ordinance. However, in reality, noise from turbines does not propagate independently, but cumulatively, meaning that the noise from each of the individual turbines is additive. And to represent this, we updated our machine learning algorithm and plant layout routine to account for this cumulative noise. So I'm going to walk through the figures on the right now, which the residential buildings are gray dots, and they're highlighted in purple if a violation of the sound ordinance occurs, while the black dots are wind turbines, and the colored surface is the sound emission as modeled by our machine learning process. The single turbine noise optimization, shown in the middle panel, has many violations of the ordinances when evaluating noise at the reality of plant level considerations. And so when we optimize with the plant level sound consideration, we can see that the picture is quite different. In fact, it reduces the number of turbines that we can place in this given grid cell by nearly half. So significant sound ordinances can have significant impacts on developable capacity, especially when they're restrictive, like this 35 decibel example here. Although from our compass collections, we found that the national average is closer to 50 decibels. And sound ordinances are not just important considerations for wind, but also for data centers, with noise from cooling and potentially on-site generation. And so with that, I'll hand it back over to Galen to tell you a little bit more about our data center siting tool.
Thanks, Gabe. So you all might have seen this map. We posted this on LinkedIn. It got a lot of attention. And then we posted it on our website. This was where we started, was just mapping out where existing operating data centers under construction, and planned data centers from a data set called Backcell. And then we overlaid this with some of the key infrastructure. So transmission, obviously, and fiber optics, and then also looking at major population centers, which where we do see some concentration historically of data center development. So this was just kind of a grounding exercise, but it was a very popular map because it just illustrated this for the first time in a geospatial context in a very understandable way. Next slide. So since then, we have extended our siting model to represent data centers. And so this is an active space that we are working. We're still working on refining this model, but essentially we're drawing on the capabilities we developed for generation technologies to do the same type of siting feasibility for a large load for data centers. And so on the left, you can see here our national scale map. And you can see data centers scaled by their capacity, their load. And then we have two different categories of where we're excluding. So everywhere that's black is non-developable from our spatial exclusions. But then again, drawing back on the multi-resolution of the model, we're able to eliminate parts of land based on things like setbacks, areas that you couldn't build in. But then when we aggregate that up, we have areas that are partially developable. And so this just means that you could get smaller areas of land, but you wouldn't necessarily be able to put these huge, large campuses. And then we have in the kind of solid, deeper blue, the fully developable areas. And so these are the areas where you're going to have more land available and potentially could build larger facilities. And when we dig into this, we actually see a lot of correlation where in some of the areas that are partially developable, you're seeing smaller data centers, and where it's fully developable, you are seeing some of those larger facilities. However, again, this is kind of an early stage work. We've got a lot more to do here, but I just wanted to highlight kind of how we can take these capabilities and start looking at new technologies, which is what we're really excited about doing. Next slide. So then the next part of this work was then to use a random forest model, so develop a predictive model for site favorability. And so what you're seeing here on the left, in the bottom left, you can see the key there. And so we're showing the 90th percentile of developability, if you will. We're also showing, again, operational data centers as those open circles scaled by their load. And then in gray, the areas that are excluded. And so this is bringing together several different factors to understand where we have more favorable conditions for siting data centers. And in this model, we evaluated the feature importance. And as you would imagine, some of the most important features are distance to natural gas infrastructure, distance to substations, distance to existing generators, distance to fiber optic networks. And so this model allows us to take all the spatial data that we have and look at some different ways of evaluating that site favorability for new data center development. And when we look at this, it's interesting. You really see a lot of overlap in where data centers have historically been built and where our model is predicting high favorability. Something that's very interesting about data centers, very different from generators, is data center developers often like to operate in the markets that they know best. And so, that's why like Dulles has really, the Dulles airport region, Loudoun County has really blown up just because the area has a lot of great infrastructure, and the data center developers are really comfortable operating in that space and working with the county. And so we start to see that, and we see things like places like Dallas Fort Worth also being kind of a hub that we're starting to see growth. So this is just a way for us to kind of understand some of those patterns and represent those spatially. Next slide. So drawing back to the very beginning, where I showed you the projections of data center growth from Evolved Energy Research from one of their recent studies, one of the important parts of our work has been downscaling future load and then coupling that with the Reeds model. And so the Reeds model is trying to understand, what are the needed and kind of no regret investments in the bulk power system to support the data center growth. And so we've been working closely with them, and here is just one set of data center projections that we've been using from EER. And what this shows, these bars, this is from 2030 to 2050, and showing you the progression of data center deployment that they have projected. And the tallest bar is 50 megawatts in that region. Just so you could get a sense of, this is useful, but it's also very regional. And so what we aim to do is then further refine this with the favorability model that we've developed. So keep this in mind. Gabe, go to the next slide. And so here's an example of how we can apply this. And so then we've taken our favorability to downscale those ER projections to 2050. And so here's an animation that shows you going from current to 2050, where we have used that favorability then to allocate. And this is just one realization that we're showing of how we can do this. And then we can take this downscaled, spatially downscaled load and pass it into reads, and then reads can run the capacity expansion to understand, what generation transmission upgrades would be required to support this amount of growth while meeting resource adequacy. And so again, I encourage you, all of you that are very interested in the power system space, to go back and look at the Reads webinar and also the Sienna one, and you really understand a lot of the connections that we're talking about here, where we have this integrated, suite of models that look at different things. So anyways, we just wanted to highlight some of the emerging work. We have just published a slide deck called Reveal. So Reveal is the reV extension for analysis of large loads. And so a lot more detail on this particular study there, but I just wanted to leave you with this interesting example of some of our emerging work. Next slide. Okay, so our last slide here to wrap things up. I should have mentioned we're going to get to this. I should have said at the beginning. I've gotten a lot of questions already. People are very interested in using the model and wondering, how you can run it. So as I mentioned, this is a high performance model. It's a big model. It has a lot of data inputs. There's a lot of computing, spatial temporal computing. So you can run it technically on a laptop, but for a very small area. We have a test case for Rhode Island to give you a sense. So you can easily run that on a laptop. But you want to run this for anything larger. You're going to need to run it on, some sort of cluster, an HPC. It runs really, really well. It also runs great on the cloud. We've got some developer partners, big energy companies that they're running instances of reV themselves on the cloud. So that's really doable. On the left is the landing page for our model, as well as the repository. We open source everything, but we wait until it's mature and it's been validated. So it was a question about the natural gas that we're just getting started. That will be, probably a year and a half before we publish that. But we do try to, be as timely as we can and get this out there because, people really want to use it. So a lot of the stuff, Reveal, the data center model, that is open sourced. And then pretty much everything else, except some of the emerging stuff that Gabe talked about, is in the repository. For those that, don't want to necessarily run it or don't necessarily have the compute resource to do it, we publish a standard set of outputs on our platform called Siting Lab. Siting Lab has multiple technologies, has a lot of the ordnance data, and it has our standard supply curves. So we update this every year. We work closely with the Reads team, and as they're publishing standard scenarios for the Reads model, we're publishing our standard scenarios, our standard supply curves that go into standard scenarios. So you can go to Siting Lab, and these are really easy to use. The supply curves are in CSV format. We put a lot of the information that, not everything that you can do in the model, but we put kind of what we think is the most important, most useful. So it allows you to do a lot. You can just bring that into any GIS data set, any GIS software, or, open it up with Python and interact with it. do a lot actually just in Excel to kind of understand some of the regional components, regional patterns from the site from the supply curves. Um, so that's a great resource. We also didn't talk a ton about scenarios, but we have several different scenarios that we develop our supply curves under, as far as, kind of a very unconstrained siting scenario, kind of a baseline best practices that we see happening across the country, and then a very constrained siting scenario. So you'll see those different what we call open, reference, and limited siting scenarios that will run for the same technologies for each year of our supply curves. So all of that is available. I invite you guys to look at all of these links and dig in deeper. And yeah, so we will close it there. So we have time for questions, and we'll jump back into the Q&A here. Um, great. All right, so maybe I'll just go through the ones that I haven't answered yet. So first question here, does reV now or in the future also include locations of offshore wind sites, cost of offshore HVDC lines costs, and connection to transmission on land? Gabe, this is your question to answer.
Sure, yeah, so we do. We've developed a pretty robust set of cost relationships for key offshore wind parameters like distance to shore and distance to ports and water depth, and we have a very robust offshore transmission framework that relies upon the same framework that I outlined here, with costs and frictions and exclusions, evaluating different types of cables. So all of that is available. We have work published evaluating the cost of offshore wind energy out to 2050 in the States, and we've worked on a number of offshore transmission studies in the Atlantic coast and the West Coast, which are two that were published in the past couple of years, and we're working on an offshore and coastal study in the Gulf region right now. So certainly we have a robust rev framework for offshore, both generation and transmission.
Thanks, Gabe. Um, Next question here is just giving us a bravo for the mind-blowing work. But then the question is, any thoughts on using this for mining or slash critical mineral siting? Yes, this framework we're starting to have some of those brainstorming sessions and working. We have a robust team that works in critical minerals and materials. At the lab, so we've been working a lot with them to really understand, what's the low-hanging fruit, where should we start? But yeah, exciting work that, yeah, stay tuned. We're definitely working that space, and we'll be releasing some work in the future. Next question, any coverage of Canada and or Mexico? Yes, it's been a while, but the lab led the North American Renewable Energy Integration Study. This was actually kind of how we got started with the reV model. This was close to a decade ago. And so the model easily runs anywhere in the world as long as you've got the input data. So actually, Canada and Mexico, the lab produced wind and solar data sets. So the NSRDB covers almost the entire world. So that's no limitation. The Wind Toolkit, we developed a Canada and Mexico data set that are publicly available through our web platforms. And so that can be very easily run. It's also available on AWS. So yes, you can run reV for Canada or Mexico. We don't currently publish any supply curves because we just don't have any active work. So we don't have anything up to date, but it's absolutely possible. Next question, when you say geothermal, I'm assuming it includes EGS. Yes. Enhanced geothermal systems is obviously kind of the main focus of our geothermal work. We develop hydrothermal supply curves, since that's really, the current technology that's very, tried and true. But we're seeing rapid advancement in EGS, and so that's an area that we're putting more of our focus on. So we have a couple different areas, thrusts of research. The first is on the resource uncertainty. So the geothermal subsurface resource obviously has much higher uncertainty than we do in other resources that we model with reV. And so understanding that uncertainty and being able to bound it and look at kind of some different scenarios exceedance probabilities of that resource is a part of it. The next part we're looking at that is really developing all of our siting scenarios to represent kind of rapid and massive deployment of EGS systems. And so, yes, and that's actually already available. Those are published on Sighting Lab. So you can go out and you can get the hydrothermal and the EGS supply curves. We're actively working on those and we'll be releasing updates the end of this fiscal year. Um, so yeah, definitely doing a lot in the hydrothermal space. Or sorry, in the geothermal space. Um, let's see. Would in the future rev change the data format type? Like moving from H5s to net CDFs. We have talked about that a lot. H5s really work quite well. I guess it really wouldn't be too hard to, if you're taking the H5s, the time series data from Sighting Lab, those can be converted. I guess, that's a good question. So maybe it's worth us thinking about developing some tools to interface. I encourage everybody also who's really, in the weeds on the code base to look at RevX and Rex. We have a couple different interface toolkits that are ancillary to Rev that enables you to interface with the resource data to do a lot of the aggregation and kind of data processing side of things. So there's a lot of tools in there. But we don't have current capability, but I appreciate the question. Something that we've definitely been talking about. All right, next question. Have you integrated this into blackout data and grid resilience metrics? So that's not necessarily the space of Rev, but absolutely that feeds into it. So the Rev model is coupled to a lot of our resilience modeling, where we are looking at things like outages and different hazards that will take different assets off of the grid and then understanding kind of what the responses are. So those are modeled more in our resilience side of the lab, but Rev provides a lot of the siting and the generation data that go into that. So yes, but this in another space. Um, how do you navigate utilities not wanting to share their network data, and how do you get around to it? So this is a great question. Companies are obviously protective of their sensitive data, of their, what's really important for them to have control over. We totally understand that. Obviously, it makes things hard in the, open data, open source modeling space. We do have really good data that we license on the location and rating of lines and substations. We've got some good fiber optic network data that we have. We've got good pipeline data that we're now starting to use for natural gas. So, you know, we navigate it the best we can. One thing that's great about the lab is we have, ongoing collaborations with most of the utilities in the country. And so we do a lot of work with them, but we respect the fact that they don't want to publish all of their network data. So, yeah, it's a challenge, but we've got some ongoing work right now, creating synthetic feeder networks on the distribution side, so that we can represent that infrastructure within our models. So that's kind of one of the ways that we get around that. And then maybe one of the other big pieces that I would mention is hosting capacity, the available transfer capability at substations and on lines. That's not something that's easy to get at, and so we're doing a lot of modeling to be able to represent, how much capacity you potentially have at a substation. Obviously, that's kind of it's a holy grail question. That's a really important, really hard one. But we are actively working on that. Um, Last question. How did you architect all this? Such a great example of modularity, interoperability. Hey, I love the question. So, I actually was one of the original developers of Rev. I'm not a model developer. I'm a geospatial data scientist by training. And this was during the NERIS project. And so, me and my colleague Nick Grew and Anthony Lopez, we were the three that did the initial coding on it. And yeah, it was we learned a lot. After a couple years, I brought in a formal software development team, and we basically took the prototype that I wrote, put it aside, and started from scratch. That is probably, that is why the model is so robust now, is because we had kind of that, let's figure out what it needs to do, and let's like understand what our challenges are going to be, and then let's do it right. And so, this is something that I really advocate for. generally when you're building models, Gabe and I, we lead the research, the R&D, like algorithm development, but then we have a lead developer who's really brilliant, and the way he structures and architects the model makes it very flexible and very extensible, which is really important because we're constantly bringing in new technologies and new capabilities into the model. So yeah, it's a big effort. But I really appreciate the question. That's in kind of the nuts and bolts. And for those of you that do dig into the code base, I hope that you'll appreciate that. We've really tried to make everything modular and make it so that you can use the different pieces. And that's something I mentioned. We've got a lot of pieces that people will just use on their own, like interfacing with the Win toolkit or the NSRDB. Maybe you just want generation profiles. You actually don't need the full supply curves. You're not going to look at siting. You can easily do that. And so, yeah, we've designed the model to be really flexible. And then maybe on the broader users, we also provide kind of summaries of that as well in like CSV format on Siting Lab, so you can download it and you can just grab the capacity factors. You can grab the capacity factors and look at what impacts that has on kind of a very localized area. So we try to make it as usable as possible.
One thing I'd tag onto that is that every year we publish annual updates that sort of summarize this in textual form as well as graphical form. So you can pull a lot of figures and information there. And that's an effort that's done, by a team of, I think there's 15 authors on that paper. And I think that just highlights some of what Galen was saying about the massive amount of effort and number of people that are involved in making reV the tool that it is. It's not just me and Galen, and it's not just our lead software developer, Paul Pinchuk, who's awesome, but we have a team of 5 analysts, and then we have people on all of the downstream models that we work with. And so big shout out to them. They're doing great work in enabling us to keep producing these sorts of really impactful and important and integral data sets that can be used throughout the energy systems modeling.